there exists a distinct primordials P1 and Q1. P1 and Q1 are other primordials. P subset are equal to P1, subset are equal to Q1, subset are equal to Q. And there is no primordials properly between P and Q. No primordials between properly Q. This theorem is proof. Okay. So this is a theorem is. So what is? Let S be a classes of chain of primordials between P and Q. S be a chain of. This is the set of all classes of classes of chain of prime ideals. So prime ideals between P and Q. If P is equal to, we can take the set of all I such that I is a prime ideal. So P subset are equal to I subset are equal to Q. P subset are equal to I subset are equal to Q. So S is the classes of chain of ideals P. Ci is a chain of S. So like that. Is it clear? The S is the chain that the arbitrary union of I belongs to cap is a Ci. Is also a chain. Is also a chain in P. Is a chain in P. And hence says applying the John's lemma. Yes, applying the John's lemma means John's lemma is applying the John's lemma is a maximal number. Say, see, this is John's lemma is called a chain. It has a maximal element. It is also first of all poset. It has a chain and also it is a greater maximal ideal. Say C, the primordial between Q and Q. So what happened is P subset are equal to I subset are equal to Q. So and but not belongs to I does not belongs to C. So therefore C union a singleton I. C union singleton I. So not a chain. Also P comma Q belongs to Q. P comma Q belongs to C. Since C union P comma Q is a chain in P. Choose an element A belongs to Q such that A does not belongs to Q. Choose an element A belongs to Q. So A does not belongs to P. This is a positive. P subset are equal to. And what is P subset are equal to Q and approve? A belongs to P, A does not belongs to Q. So this is C1 is equal. This is a I is a belongs to C such that A does not belongs to I. C2 is equal to J belongs to C such that A belongs to J. So C is equal to C1 union C2. C1 intersection C2 is equal to designed. So designed. So P belongs to C1, P belongs to C1, Q belongs to C2, I belongs to C1, P belongs to C1, Q belongs to C2. Also, I belongs to C1, J belongs to C2. J subset not equal to I also. Now it's a clearly since C is a chain. Since C is a chain. Since C is a chain. In I subset are equal to J. Next it is called is P1. P1 is equal to U arbitrary union. I belongs to C. So I belongs to C such that A does not belongs to I. Is a union of C1. Same Q1 is equal to also intersection. J belongs to C and A belongs to J. Intersection is a intersection C2. So where C1 and C2, where C1 and C2 are chain. So P1 comma Q1 primordials of R. A belongs to Q1, A does not belongs to P1. Since every member of C1 is contained in every member of C2, we have P1 subset are equal to Q1. So P subset are equal to P1, subset are equal to Q1, subset are equal to Q. So like this. So this is a theorem is P1 Q1 is a between no maximal ideals or no prime ideals are there. So next is one definition. So it is also the constructing prime ideals without using multiplicity closed set for any ring or let annihilator of A is equal to x belongs to R such that AX is equal to 0. AX is equal to 0. Annihilator of A, x belongs to R such that AX is equal to 0. The ideal of R fact annihilator of A equal to 0. Now, theorem in 2.5.1. So, what is the 2.5.1 theorem is statement? P be an ideal of a ring R such that P is a maximal member of the classes of all annihilator ideals of non-zero element of R. Then P is a prime. So let S is equal to, this theorem is proof is, let S is equal to what happened? Annihilator of A is such that A not equal to 0 belongs to capital R, non-zero element of R. Annihilator of A, S is equal to. We have to give an P is a maximal member. P is maximal member in S. Let P is equal to annihilator of B, okay, such that B not equal to R belongs to R. So since B not equal to 0 belongs to, comma, 1 belongs to P. Connection. కంపెనీకి ఏమైనా పైసలు ఇస్తాను ఏమన్నా అన్నదా కాదు అన్ని ఒక్కరినే చేసిన అంటున్నాను అట్లా. సో దిస్ ఈస్ P is a proper ideal of R to prove that is a prime. P is a proper ideal of R to prove that. P is a proper ideal of R. P is a proper ideal of R to prove that it is a prime. So prime definition, what is x comma y is a belongs to R such that xy is a belongs to P, that is xy belongs to P, then B of xy is equal to 0. Annihilator definition. So since x does not belongs to P, then P is equal to annihilator of B. B of xy equal to 0, annihilator of B. Subset are equal to annihilator of Bx. And Bx is not equal to 0. And hence maximality P, annihilator of Bx is equal to P, which is implies y belongs to P. So y belongs to P since let us all ideals of R a ring are finitely generated, that is I is equal to generated by x, finitely generated, where x is a finite subset of R, x is subset of R equal to R. Every element of I is the form R1 x1 plus R2 x2 plus Rn xn, where Ri belongs to R, x is equal to x1 x2. 2.5.12. So next is 2.5.12 theorem is same thing. P is an ideal of a ring R. Suppose P is not finitely generated, maximal among all ideals on R, they're not finitely generated, then P is a prime. So proof. So first to observe that since P is not finitely generated definition, it is a finitely generated is equal to P is equal to generated of x. Not finitely, it is not equal to. P is not equal to finitely generated of 1 is equal to R. So let A comma B belongs to R. So such that AB belongs to P. So AB belongs to P. So AB belongs to P, and suppose B does not belongs to P. So then P plus RA is a ideal. P is ideal, RA. P is ideal, RA. RA is a means a generated of small a. Generated of small a is ideal. But P plus RA is also ideal, properly containing P. By maximality of P, it is follows that P plus RA finitely generated in pick of elements. So what is the pick of elements finitely? P1 plus R1A, comma, P2 plus R2A, comma, up to son Pn. So what is the pick of P1 plus? So P1 plus R1A, comma, plus P2 plus R2A, comma, Pn plus Rnj. This is the pick of elements. So what is the pick of elements is now P1 plus. So this is P1 plus R1A, comma, P2 plus R2A, comma, so P1 plus R2A, comma, P2 plus R2A up to son. Pn plus Rn of A. So these are where Pi, where is P1, comma, where is the Pi belongs to capital P, and indirectly it's mean P1 comma P2 belongs to P. Where is Ri? Ri is a belongs to R. Nothing but R1 comma R2 belongs to capital R. Such that symbol. I'm to write here. P plus Ra. P plus Ra is a generated by. So generated by the set. Generated by the set. This is P1 plus R1 of A, comma P2 plus R2 of A, comma up to some Pn plus Rn of A. So Rn of A. Let I is equal. This is I is equal. X belongs to R such that XA is equal to XA belongs to P. XA belongs to P. Then I is ideal of R. I is already is an ideal of R. Is an ideal of R. I is ideal of R. So P subset R equal to high, comma B belongs to high. So now also since B does not belong to P, I properly contain P. Again, the maximal at P. So I is finitely generated. I is the finitely generated is generated by X. And X is equal to what is X is equal? This is a small x1, x2 up to some. This is a XM. So XM. So it is XM. Now it's a clear XM. Now we to show that it is a clear. Now we claim that now we claim that now we claim that oh, now we claim that now we claim that now we claim. So this is a we claim that P is a generated by is generated by so is generated by the finite set. What is the finite set? This is the finite set is P1 comma P2 comma up to son Pn comma x1 a comma x2 of a comma up to son xm of a. So xm of a. So which is a contradiction. This is a contradiction. Since P is not finitely generated, this is a finitely generated. కానీ మనం తీసుకునేది ఒరిజినాలిటీ is P is not finitely generated in high. So that is not the established. Either A belongs to P or B belongs to P. In name this you can show me AB belongs to P. We can show me A belongs to P or B belongs to P. And then P is a prime ideal. P is a prime ideal. This is the prime ideal definition. A belongs. To prove the P is a generated. Next primer. To prove the P is generated by the set P1, P1, comma P2, comma Pn. So what is the P is generated by the set? This is generated by set is P1, comma P2, comma up to son in Pn x1 of A, comma x2 of A, comma up to son xn of A. This is generated by A. So xn. Now first note that P1, P2, P2 belongs to P. So P x1 of. So what is P1 comma P2 comma up to son Pn is belongs to P and x1 of A comma x2 of A comma up to son xm of A belongs to P. So xm of belongs to P. So each xi is belongs to P. This is a premium. So now we let y belongs to P. So it's the since generated by P plus Ra and y is subset R equal to P. Subset R equal to P plus Ra. P plus Ra. P plus Ra. We write y is equal to. So we write y is equal to summation of I is equal to 1 to n Si. So Si of Pi plus Ri of A, R of F. For some S1 So, mm, so next right here, summation of I is equal to 1 to n, Si of Ri is equal to summation of I is equal to 1 to m. So Tj and Xj. So Tj belongs to R. హాఫ్ అన్ అవర్ అయిపోతే సార్ దగ్గరికి వెళ్తాను వెయిట్ చేస్తే ఇక్కడ రెస్ట్ తీసుకో. So where since x1 comma x2 comma up to so on xm is a generated by I. So generated by I. I is equal to is a generated by capital X also. Now it is a y is equal to, therefore y is equal to also can be written as S1 P1 plus S2 P2 plus up to so on. It is SP SCN PN. This is generated by P. Remaining elements T1 X1 T1 X1 plus T2 X2 plus up to so on. So this is TMXM of A. So these elements T1 X1 of A, T2 X2 of A up to some TMXM of A. So P is generated by P1, P2, Pn, X1 of A, X1. So P is generated by, this is generated symbol, P1 comma P2 comma up to so on in Pn. So Pn. Next is X1 of A, this is X2 of A up to so on Xm of A. So this we proved that A comma B belongs to R. This implies AB belongs to P, implies A belongs to P or B belongs to P. So hence, therefore, P is a prime ideal. Hence, P is a prime ideal. So this is the prime. So it is a completed of 2.12 theorem. Next to 2.13 theorem. 2.13 theorem is not important in left them. So by using this 2.14, 2.514 theorem is now this is a 2.514 theorem. 2.514. So 2.514 is let P1 comma P2 comma Pn be a prime ideals. Let P1 comma P2 comma up to son Pn be a prime ideals. Be a prime ideals. So be a prime ideals. So prime ideals. And I be an ideal of R. I be an ideal of R. So ideal of R. So high subset are equal to P1 of union, P2 is a union up to son in Pn. So this is then prove that I subset are equal to P1. So for some I, this is a statement we can prove. So మనకి ఇచ్చిన given statement is P1, P2 prime ideals. I is a ideal of a ring R. I subset of P1 union P2 union Pn. So I subset are equal to Pi is a for some I. So it is a I subset are equal to Pi and a arbitrary union is there. Now first time we prove the by the theorem is mathematical induction. So by trivial n is equal to 1. N is equal to 1, the theorem is true. What is the theorem is? I subset are equal to. So union of I is equal to 1 to n P I. Its a meaning is I subset are equal P1 union P2 union Pi. So for I is equal to 1. So I is equal to 1 at what happened? I subset are equal to only P1. That I is equal to 1, the theorem is true. So n is equal to 1 or I is equal to 1, the theorem. Suppose n greater than 1, assume the theorem n minus 1. So n greater than 1 is I not subset are equal to P1 for all 1 less than or equal to I less than or equal to n. This is not. We shall prove that. So contradiction. We shall prove that. So what is the shall prove that? I is not subset or equal to. So arbitrary union of I is equal to 1 to n in Pi. So in I is subset or equal not equal Pi for any I. Q is equal to other prime ideals. Arbitrary union of J is equal to 1 to in Pj. So by induction hypothesis, I is not subset or equal to Q1 and I not subset or equal to in Pj. So in Pj. For whenever is J not equal to I, thus theorem. For any I choose Now again, A is an element of I. AI is belongs to I, and AI is does not belongs to Q. Does not belongs to Q. Since AI does not belongs to indirectly PJ, so in PJ, so that is called is A does not belongs to AI does not belongs to in PI. So PI. This is called is done for some I not. Then compulsory A does not belongs to PI. So nothing but A does not belongs to arbitrary union of I is equal to 1 to n. PI is also. Only A does not belongs to PI. A1 not equal to belongs to P1. A2 not belongs to P2 up to so on. AN does not belongs to PN. So it is a union is also. AI does not belongs to P1 union, P2 union up to so on PN. A P1 union, P2 union, PN also. And AI belongs to high. So and AI already AI belongs to high. Therefore, high is subset or equal to. So I is subset or equal to indirectly arbitrary union of J is equal to 1 to n in Pj. So that's by using assumption. Otherwise, therefore AI belongs to I. Otherwise, this means AI belongs to P. So only it is AI does not belongs to P key. It is a this one. It is otherwise this means AI belongs to P or all I. So what is a B is equal to can be written as summation of I is equal to 1 to n. So A high comma A high A1 A1 comma A2 comma up to son A high minus 1 A high plus 1 up to son AN. So this is called B belongs to high. So B belongs to I. Since AI belongs to capital I, for all I belongs to for all I. So B belongs to PI. P does not belongs to Pi. So for all I. So then otherwise is B belongs to Pi. So it is meaning is so A1 comma A2 comma up to son AI minus 1 AI plus 1 AI plus 1. So up to son AN is equal to B minus of summation. So J not equal to I. J not equal to I. So this is A1 comma A2 comma up to son AJ minus 1 AJ plus 1 up to son AN is a belongs to P. So therefore, which is a contradiction? This is a wrong. 100% AJ does not belongs to Pi. So for all J not equal to I, compulsory I is subset or equal to union of I is equal to 1 to n. This is a Pi. So union of is equal to Pi. Now again, this is a theorem is 2.5.11. In 2.5.15, so 2.5.15 theorem, the arbitrary intersection. I1, I2 ideals of a ring are I1 intersection. So this is I1 okay, ideal, I2 is one ideal, I3, this is In of ideals of R. So I1 intersection I2, I2 intersection I3, up to so intersection In. So intersection subset are equal to P. So I is subset are equal to P for some I. So P is equal to I1 intersection, I2 intersection up to son In intersection of In. So therefore P is equal to P is equal to II. So then P is equal to for some I. So for some I. So this is the theorem proof is. So it is a proof is I1 subset are equal to P, I1 subset are equal to P for all I, each I. We can choose AI is a belongs to capital II. So AI does not belongs to P. So this is a subset definition. One element of first one, second element is not. Then product is A is equal to can be written as. What is the product is A1, A2 into AN. This is A1 is belongs to I1, A2 belongs to I2, AN belongs to IN. The arbitrary intersection. I is equal to 1 to N. Arbitrary intersection is II. So and A does not belongs to P. So this is the meaning I1 intersection I2, I2 intersection I2 up to so on. Now, so then I1 is subset or equal to P. So for some I. Now, okay, this is the now again it's a close now. Next is Oh, we learn in a topic is it is the same way. In general topic is unique factorization domain. So an integral domain, we say that is unique factorization domain. A non-unit element can be expressed as product of so R plus comma dot is a ring. This ring is integral domain. So already integral domain is commutative ring with unity, commutative ring with unity. Now, commutative ring with a commutative ring with unity, no zero divisors is called is integral domain. So this integral domain is said to be unique factorization domain. Unique factorization domain. So a integral domain is said to be unique factorization domain. The integral domain is a unique factorization domain. A integral domain is said to be unique factorization domain. So it is called as a non-unit element can be expressed as a product of a prime. A non-unit element can be expressed as a product of finite number of prime elements. So every irreducible element is prime element. So first one is a non-unit element. A non-unit element. A non-unit element can be expressed as a product of finite number of a non-unit element can be expressed as a product of finite number of irreducible element. Second condition, every irreducible element is a prime element. Every irreducible element is a prime element. That is called as a comma b is a belongs to D. P divides of AB then implies P divides of A or P divides of B. This is a prime element definition. So it is called as unique factorization. The theorem is called as 2.5.616. What is our first of all? R plus comma dot is a ring is said to be integral domain. A commutative ring with unity, it has no zero divisors, is called integral domain. An integral domain R plus comma a commutative integral domain with unity is said to be unique factorization domain. First condition, a non-unit element can be expressed as a finite number of irreducible factors. Finite number of irreducible factor. Second one, every irreducible element is a prime element. That is called is uniform. Every irreducible element, prime element is means P divides of AB implies P divides A or P divides B. Next to 2.516 theorem. DBA integral domain. DBA integral domain. So if P is a element, P non-zero element of D, P non-zero element of D, then P is a prime element. P is prime element. This is a prime element. P is a prime element. So if and only if, so principal, if and only if, the principal ideal of DP is a, the principal ideal, the principal ideal, the principal ideal, the principal ideal. So the principal ideal is DP is a prime ideal, is a prime, is a so prime ideal is a prime ideal of D, is a prime ideal of D. So it follows that. So for any A belongs to D, A belongs to D, A belongs to D. So A belongs to DP, A belongs to DP. So this is if and only if P divides of A. So P divides of A. So that dP is equal to D. So if and only if P is a unit, P is a unit. So is a unit. In fact, that A is element of DP. A belongs to DP is called is principal ideal. So if and only if every principal ideal is if and only P divides of A, and DP is equal to D. D is equal to if and only P is a unit. So next is 2.17 theorem. D be an integral domain, then D is unique factorization domain if and only every non-zero prime ideal contains a prime element. Every non-zero element contains a prime element. This is important also. Now, if and only if. First of all, D be an integral domain. So, E integral domain and D is a unique factorization, a UFD, unique factorization domain. If and only if every non-zero element, every non-prime element, every non-zero prime ideal. So prime ideal, prime ideal prime ideals contains a prime element, So prime element. So this is a DB and integral domain. D is unique factorization domain if and only every non-zero prime ideal contains a prime element. So prime element. This is a proof. So it is a proof. It is a clear. Suppose D is suppose D is a unique factorization domain. AUFD. The unique factorization domain. Let P be a non-zero prime ideal. P be a non-zero prime ideal. So non-zero prime ideal. So non-zero prime ideal of prime ideal of D. So prime ideal of D. Non-zero prime ideal of D. So since P not equal to D, every element of P, every element of P, every element of P, so every element of P is a non-unit, a non-unit, a non-unit. So this is non-unit. So non-unit is means P not equal to a singleton zero belongs to D. We can an element. So we can element here such that a non-zero can be product of prime element. A product A is a non-zero element of P. So this is a every non-unity element, a product of finite number of prime element, a product of prime number of. So that is A is equal to P1 comma P2 comma up to some Pn, where each each pi is a prime element, is prime element, each prime element. So each prime element. Now, since I am taken, since A is equal to P1 comma P2 comma up to son, Pn is a belongs to capital P, is a capital P. So and P is a prime element, and P is a prime element. P is a prime element, prime element. So P is a prime ideal. P is a prime ideal. So it follows that. So P is a prime. ఇక్కడ మనకి ఏం చేయాలి? ఈ contains is a prime ideal, contains a prime element. Prime element నుంచి we can show me A is equal to P1, P2 belongs to capital P. So this is a Pi. Each where P1 is a prime element, P2 is a prime element, Pn prime element. This is a P1, P2 belongs to capital P. What is the capital P? Capital P is a prime ideal. Capital P is a prime ideal. So this is a proof. Next is conversely. Now it is a conversely. What is a conversely? This is a conversely. Conversely, suppose every non-prime ideal D contains a prime element. Suppose every suppose every non-zero prime ideal, every non-zero prime ideal D, so prime ideal D contains, so prime a prime element, so a prime element, let T be the set of all, let T be the set of all, let T be the set of all let T be the set of all, let T be the set of all, let T be the, so T be the set of all, be the set of all, be the set of all product. So all product of finite number of finite number of finite number of prime mm, prime element prime prime element prime element in D. So this is, let us suppose set of all product of finite number of prime element in D. So we shall prove that. We shall prove that. We shall prove that. What is the proof that we shall prove that? T is a structured multiplically closed in D. Structured multiplically closed in D. Or structured multiplically closed means T is a T is a structured multiplically closed means T is a closed multiplicative closed or T is a closed T is a closed with respect to multiplicity, with respect to multiplicity. So multiplicity. Let A comma B. So this is, let A comma B belongs to D. A comma B belongs to D. So A comma B belongs to D such that, so such that AB belongs to T. AB belongs to T. So AB belongs to T. Then we write AB is equal to P1, P2 up to so on in Pn, where each Pi is a prime element. Now P1 being a prime, it should be divided either A or B. So P1 divides A, P1 divides prime. P divides AB, either P divides A or P divides B. Since P is the prime element definition, P divides of AB, P divides A or P divides B. Suppose P divides of AB, this implies P divides of A or P divides of B. We choose P divides of A, choose just then A is equal to, then P divides of A is equal to, then A is equal to P high. So this is a P1 divides. Suppose P1 divides of AB. And P1 is a prime element, P2 is a prime element. We choose P1 divides AB. P divides of P1 divides of A, P1 divides of A. P1 divides of A is equal to P1 into something. What is the P1 into something is? P1, it is a P1, it is a A1. So P divides, so A1. So for some A1 belongs to D. A1 belongs to D. So A1 now we can do P1 A1, both side AB product. So AB is a product is called P1 A1 B1. So P1 A1 B. So A1 B AB. So AB is equal to already. Like this is P1 of A1 of B is equal to AB. So we can do right here. P1 of A1 of B is equal to B is equal to AB. So AB is equal to already P1, P2 up to so on in Pn. So Pn. Since D is integral domain so that what is A1B? A1B is equal. So next time, okay, second element తీసేస్తాం. So what is the ఇక్కడ P1 A1? So P1 of AB is equal to P1, P2 up to so on Pn. ఇక్కడ P1 cancel అయింది అనుకో indirectly. Left hand side వస్తుంది. What is the A1 of B is equal to? Zero divisors అంటే we can do. So P అంటే we can take left side అంటే P1, P2 of P1 of AB minus of P1, P2 up to so on in Pn is equal to 0. P1 is common, AB minus P1, P2, P2, P3, up to so on Pn is equal to 0. D is a integral domain, has no zero divisor, P1 equal to 0 అని ఉండాలి. AB minus P2, P3 up to so on Pn equal to 0. And this is not equal to 0, non-zero element కాబట్టి it should be AB is equal to P2, P3 up to so on in Pn. P2, P3 up to so on AB is equal to P1 common is AB minus P2, P3, Pn equal to 0. P1 not equal to 0, what we know that AB minus P1, P2, P3, Pn equal to 0. AB is equal to P2, P3, Pn. AB is equal to P2, P3. This is induction. Use induction to prove that A1 or B. So A1 or B. So like that. A1 of or B. A1 or B. So it is a clear form induction. A1 of B is equal to P2. Uh, A1 of B is equal to P2, P3 up to so on in Pn. So A1 or B is in capital T. Therefore, A or B in cap is in capital T, is in capital T. So is in capital T. So thus T is a structural multiplet closed in D. So therefore, is a prime ideal in D. Now A is a it is called is A be a non-zero non-unit element. So what is our now next second? Let A be A be a non-zero, 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 and a non-unit element, non-unit element. So non-unit element in D. So in D. So A does not belongs to T. A does not belongs to T. So then A belongs to R of T. R. Therefore, there exists a prime ideal P. There exists a prime ideal P. Prime ideal P. Prime ideal P. So prime ideal P such that A belongs to P. A belongs to P subset R called R of T. So R of T. By hypothesis that prime ideal P should be a contents is a prime element. It will be in T. So contrast. This is A belongs to T. Every non-zero non-unit element D can be written as product of finite number of elements. The uniqueness of this product can be proved a or routine by this one. It is a leftover this way. So it is the theorem is so it is there exists a prime ideal P. Every prime ideal containing a prime element P. So which will not to be in T a contraction. This is A belongs to T. A is a belongs to T. This will be A belongs to capital T. This is called ism. Now, A belongs to Q. Every non-zero and non-unit element D can be written as a product of finite number of prime elements. So, this is the theorem is close 2.5. 2.5.18. So, let IB is a primordial of ring R, P to pure of I. So, is a one-to-one correspondence between primordial of R containing I and the primordial of R over of I. So, P to P over of I is a quotient ring. So quotient ring elements is a formation P over of I is equal to X plus I such that X is a belongs to P. So X belongs to P. So X P P X P over of R over I X plus I X belongs to P. Now this is you can easily that P containing ideal. So R is if and only P plus I is a prime ideal R over of I. So it is okay. This is the integral domain. Prime ideal of R if and only for P plus I is a prime ideal of R over of I. Next is 2.5.19. This is also a proper ideal of R. I is a prime ideal if and only if R over of I is the integral domain. So it's already One is the trivial. One is the trivial is what is the one is the trivial is called is uh, first one is R o I is subset or equal to R over of I. R over of I. So this is a proof R over of I is simultaneous is a trivial. So I subset or equal to P. I subset or equal to P. This is if and only if R over of I to P. So if and only if I subset or equal to P or J subset or equal to P. So if and only if I intersection J is subset or equal to P from, so it is a 2 and third is close. I intersection J, so subset or equal to P. 4 follows from 3. So I belongs to I. So 1 belongs to I if and only if 1 belongs to R over of I. Okay. Now, since I subset are equal to I subset are equal to R over of I, so J subset are equal to R over of J. So I plus J addition, I plus J subset are equal to R over of I plus R over of J, R over of J, and R over of then R plus R over of I plus J subset are equal to R over of R over of I plus radical of R over of J. So J. So same thing. I subset are equal to I plus J. J sub J. So therefore R over of I subset are equal to R over of I plus J. I plus J. R over of J subset are equal to R over of I plus J. So and hence. So it's a clear. Now it's a clear from R over of I plus R over of J. So in subset are equal to R over of I plus J. So it is equal to R over of I plus J. So I plus J. This is a close. Now 6 is a completed. Now I is a prime is equal to I is equal to R over of I. So R over of I. 7 from 2, 6. I subset are equal to J. It is clearly R over of J. I is subset or equal to R over of J over of I. It's a quotient ring. Let X plus I is a belongs to R over of J, radical ring of J over of I. So this is X plus I is a whole power of N. It belongs to J over of I. So J over of I. So N greater than 0. It's a X power of N minus A belongs to I. So and A belongs to J. X power of N minus A belongs to I intersection J. So this is X power of N belongs to J and X power of N belongs to R of J. So R over of J over of I is equal to R over of J. So it's I. So this is equal from SAQ 2.23, 24, 25. 2.23. So let n greater than 1. So nz is equal to an such that a belongs to Z. Okay. Is a proper ideal of Z. Is a proper ideal of. Is a proper ideal of. Is a proper ideal of Z. Proper ideal of Z. So for any B belongs to R. B belongs to NZ. So if and only if N divides B, N divides B. So NZ is a prime ideal. Is a prime ideal. So prime if and only if A comma B belongs to P. So N divides of AB implies N divides of A or N divides of B. So which is a equivalent to saying a prime element, which is a saying a prime element. Now, so it is a 24, 2.5, 24 also. Any greater than when determine all prime ideals of the ring Zn, Zn by Zn, prime ideal Zn by Z by Nz, ring of Zn or Nz. So in prime ideals, we can prime n is equal to prime element. N is equal to can be written as P1 power of N1 in P2 power of N2 distinct to prime numbers. So Pk power of Nk. This is any number can be written. Where P1 comma P2 comma are distinct to primes. R1, R2, Rk are positive integers. So Zn is isomorphic to Z by Nz. So Z by Nz. So Z over of N is isomorphic to Z by Nz. And hence prime ideal of Zn. And hence prime ideal of Zn are precisely principal ideal of in Zn generated by P1, P2, Pk. So the prime ideal of so and hence prime ideals of corresponding to prime ideal of Zn is containing from non-zero prime ideal of Z are precisely principal ideal generated by prime number P also Nz. Nz is subset or equal to Pz, Pn, Pn. So Pn. So if and only P divides N. So P divides N. The prime number of prime ideals of Zn, so precisely principal ideal of in Zn generated by P1, P2, Pk. So P1, P2, Pk. It's also remaining. It's also kind 25 determine R over of radical of N over of Z non the radical of zero ideals. Special importance of the following this special name of this. Now, okay. Okay. ఎవరిది బాబుగా మైండ్ ఏడిది RB a ring A belongs or A set to be nilpotent. Nilpotent definition. What is the nilpotent is equal to A power of N equal to 0. A power of N is equal to 0. Some positive integer N belongs to Z plus. So the set of all nilpotent elements of R is called nil radical of R. Nil radical of R and is denoted by N of R. Nil radical of R is denoted by N of R. N of R is equal to 0. N of R equal to 0. R is a called semi-prime ring. R is called is semi-prime ring. What is the nilpotent element is? R is a ring. A belongs to R. A said to be nilpotent. if a power of n equals 0, n is a positive integer or natural number. This is a nilpotent term. Some positive integer. This set of all nilpotent elements. R is called nil radical. This set of all nilpotent element, a power of n. This set of all, n of r is equal to a. This set of all a such that a power of n equal to 0. This is the nilpotent element is called. This set of all nilpotent elements of R is called nil radical of R. It is denoted by n of R. Nilpotent element is means a ring or a power of n. A is element of R. A power a belongs to R. N is a positive integer. A nilpotent element. A nilpotent element. So nilpotent element A is belongs to R is a ring. A is element of R. A power of n equals 0. Sorry, n is a positive integer. That is nilpotent element. This set of all nilpotent elements of R is called as it is called as nil radical of R. It is a nil radical of R is denoted by nil radical of R is denoted by n of R. N of R. Sometimes n of R equal 0. R is called semi prime ring. N of R equal to 0. So n of R is equal to 0. N of R is equal to 0. This is called semi prime ring. Semi prime ring. So semi prime ring. Semi prime ring. N of R precisely radical. It's 0 ideal singleton 0. We have following consequence. Now, nil radical in a ring precisely intersection of all prime ideals of R. So nil radical of R ring are precisely intersection of all prime ideals. So it is a okay. Now nil radical of R over of R over of I. R over of I, half over of I. This is a nil radical of R over of I is equal to A plus I, such that A belongs to R over of I. Actually, R over of I. R over of I definition of A plus I, such that A belongs to R. A belongs to R in place, A belongs to radical R over of I. Nil radical quotient is precisely. Next. Okay. N greater than n, 2.930, 2.5.30. N greater than 1, any integer. Prove that. Right integers of modulo n. Semi-prime. If and only any square free. Any square free is n is not multiple of square any integer. Multiple of any square integer. So that is square free. So it is a clear already. This theorem is already we know that Zn is isomorphic to Z over by Nz. Zn is isomorphic to Z by so Zn. The nil radical, radical. So is given by n of Zn is equal to R over of Nz by Nz. So Nz is equal to P1, P2 up to so on P Z by Nz. So Nz. Where P1, P2, P, where P1, P2, Pk are all distinct prime divides N. Hence Zn is semi-prime. If and only if N is equal to P1, P2, Pk. N is a square root into primes. Okay, it's a clear. Now once again, last to 2.5.13 theorem. So 2.5.13 one theorem is So R is a ring following equivalent each other. First one, R exactly, R as exactly, R exactly one primordial, one primordial. So one primordial, so one primordial. Second, so exactly one primordial. Every element, so every element of R, every element of R is either, so either a unit or nilpotent, nilpotent. So this is third one. R over of n over of R is a field. Quotient ring is a field. So what is the proof? This is first one. One implies to two. So one implies to two. Suppose R has exactly. Suppose R as exactly. Suppose R has exactly one primordial. One primordial. So one prime ideal. So this is one primordial. So one primordial. Say P. Say P. This is n over of R is equal to P. PA is any non-unit. If A is if A is a non-unit, is a non-unit. This is a non-unit. So in R, so in R, so then A belongs to belongs to P is equal to NR. So belongs to P is equal to NR. So some primordial by hence the a P is equal to NR అయితే A is a nilpotent. A is a nilpotent. Nilpotent. NR is called is the set of nilpotent elements. Okay. Uh, 2 implies to 3. Next. Now 2 implies to 3. 2 implies 3. Suppose every element of R is either unit or nilpotent. Suppose every element, suppose every element of R, every element of R, so every element of R is either a unit, or a nilpotent, a nilpotent. So a nilpotent. So if A belongs to R, A belongs to R, such that A does not belongs to N of R, N of R. A is a unit in R. A is a unit in R. So A is a unit in R. So which contains N of R. Okay. So R and N of R. And it is a proper ideals. Every prime ideals, uh, suppose every element either nilpotent, A belongs to such A does not belongs to N of R. A is a unit in R. So is unit in R. A plus N of R. So A plus N of R is a unit in R. In R over of N of R. Okay, you got. N of R.
నేను రవి ఇద్దరం పోయి తెస్తాం అవి మీదే నాదే అది
మీదే. 2 implies to 1. 1 implies to 2. 3 implies to 1. R over of N of R is a field. A field. A unit in R, it is a field. Unity means a non-zero element to multiply inverse. What is R over of N of R is a field. Every exactly two ideals, R over of N over of R. So field, every field has improper ideals. Improper ideals is meaning only field has two ideals, singleton 0 and f itself. So improper ideals is meaning r over of n of r and r itself ideals. N of r are itself ideals. So every prime ideals of r proper ideals and contain n of r. So n of r itself is the wholly prime ideals of r. Prime ideals of r. Now, so this is a close of the, this is n of r, very simple. It is a, the second topic is completed. Next you can, next Saturday it is unit 3 maximal ideal will be start. Uh, hello, 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 Lakshmi, మీ నెంబర్ చెప్పండి అమ్మా గ్రూప్. హలో, హలో, హలో అమ్మా, మీకు నెక్స్ట్ క్లాస్ ఫంక్షన్ అనాలిసిస్ అమ్మా, ఏ క్లాస్? హలో.